All right. Good morning, everyone. So we're going to continue today on our discussion of the Diels-Alder reaction. And remember, this is one of the first class of pericyclic reactions that we've been talking about that are classified as the cycloadditions. So what we're going to start talking today about is mostly the substituent effects in Diels-Alder reactions. So 24.3, this is in your textbook, and it's called substituent effects. Substituent effects in the Diels-Alder reaction. Now, so far, we've mostly been talking about the orbital aspects and how these orbitals are interacting as part of the cycloaddition reaction, but we have not actually talked about specifics of this reaction, like how quickly it proceeds or how easily it proceeds. So the standard example that we had picked most of the time, just taking a butadiene and reacting this with a simple olefin, actually turns out to be quite a hard reaction to perform in the lab. So you need very high temperatures to make this work, to overcome the entropic penalty that is associated with that. So you need something like 200 degrees Celsius, and oftentimes you need long reaction times. So 24 hours, for example, is very common for this reaction, and you need high pressures. And the high pressure basically favors then the formation of the single molecular species from two equivalents of the building blocks. So entropically, you basically favor the reaction if you run this under high pressure. And we know that the product already of this reaction is the cyclohexene. Now, as I mentioned already, these reactions are pretty harsh for conventional organic chemistry. So this requires harsh conditions. The reason that it requires these harsh conditions is that the HOMO-LUMO gap between these two partners, so the orbitals that are interacting, are too far apart in energy to facilitate this reaction at a lower activation energy. So large HOMO-LUMO gap in this reaction. Now, when you actually talk about synthetically useful Diels-Alder reactions, they are often not just the bare naked diene and dienophile, but they usually have some form of substituents arrayed around the periphery of these molecules that make this reaction more favorable. So synthetically useful Diels-Alder reactions are, and what we call this, usually polarized. And we'll come to that in just a second. So let's pick a simple example that is commonly used as a substrate in these Diels-Alder reactions. And it's essentially our butadiene again, with the only difference that now I'm attaching a methoxy group to one side of the molecule. And as our dienophile, we use something that is an alpha-beta unsaturated carbonyl. So let's say, for example, this ester here. These are kind of very, very classical substrates for these reactions. And if you take a closer look, you'll quickly realize that one of these partners is relatively electron rich. So it has an electron donating group on here. So this is electron rich. And this diene here is electron poor, because it has an electron withdrawing group on here. So if we could circle this and write here electron donating group, and this here is essentially an electron withdrawing group. So they're opposing substituents on the diene and the dienophile. And if you run this reaction, it proceeds actually fairly fast. And you get a mixture of products out of this that are characterized. Again, we expect to see the cyclohexene backbone, and then we have to place the substituents. So you get this one. And basically the enantiomer of this one, which is, you can draw it out here, is basically just the stereochemistry where these substituents come to the front. So these are basically the products that you get out of this reaction, 50% this and 50% this one. But what you don't see is the substitution pattern that places the substituents in a 1,3 position with respect to each other. So you don't get something that looks like this, for example, or, of course, the enantiomer of this. Now, this is a little bit bizarre because you could have thought that this dienophile could react either with this end forming a bond to this end of the pi system or forming a bond to the opposite end of the pi system. So it is a little bit strange at first glance that it selectively seems to prefer only these two substitution patterns, where clearly this end here reacts with this end. And let's put a square down here. This end reacts down here with the square end. And you don't see any crossover of basically the square end reacting with the circle end, right? So these are not observed as part of the reaction mixture. So it's worthwhile thinking about it a little bit, why you have this selectivity. And it can easily be derived based on the polarization that these functional groups induce into the pi system. So if we just draw this out here again, and we have the electron donating group attached to this one, and here we have the electron withdrawing group, then we can apply the same trick that we talked about already as part of the aldol reactions, the polarization of these double bonds induced essentially by these substituents. And we can start usually by just the most obvious, most electronegative atom in this chain, and which is in both cases here, the oxygen atom. So we know that this is most electronegative, so there's a partial negative charge on this oxygen. And that allows us to kind of go down this conjugated chain and assign to each of these carbon atoms an alternating charge, right? So if this is negative, the neighboring one is positive, then this is negative again, then this is positive again, and this one down here is going to be partially negatively polarized again. Now, it can do exactly the same thing on the other side where we have the electron withdrawing group. So we said that this is negatively charged. We know that this carbonyl carbon atom has a positive partial charge. And then we can go down the chain, delta negative, delta positive. And if you take a close look at this now, if you bring these two pi systems together so that the partial positive charge starts interacting with a partial negative charge at this end, so these were these squares here, right? And the partial negative charge at this position, at the alpha position here, reacts with the partial positive charge next to this oxygen here, then you get actually the right polarization that favors essentially the products that we see over here, because that places this electron withdrawing group right next to this electron donating group. So the favorable interaction is going to be the one, let's pick a different color here, is going to be the one that places the complementary charges right next to each other, right? So this gives us basically the observed products. We do not observe the opposite, where basically positive would react with positive. We don't see that, and we don't see negative reacting with negative, right? So these are the two combinations that we don't see, and those would have led to these products that have the 1,3 substitution pattern. So anytime you see substituted species like these one, it's very good to kind of just mentally build up your positive and negative partial polarization on these atoms to define which of these ends are favorably going to react with each other. Negative is always going to react with positive, and positive is only favorably going to react with a negative end. Now, this is kind of a mnemonic, but you can actually derive this from principles of resonance structures that we have talked about in the past. So if we look at the resonance picture, and we look at our two building blocks again, so the one with the methoxy group, for example, I think it's fairly easy for all of you to quickly write down the possible or some of the possible resonance structures that you can draw for that. So let's say we have a lone pair here on the oxygen. We can take this lone pair, push it in here, take this bond, push it out here, and push this one all the way to the end. And what that would give us is essentially one possible resonance structure where you now have a negative charge at the end of the pi system here. You have a double bond here, OMe, and a positive charge at this end. And if you wanted to, you could actually get exactly the species that we predicted as the polarization for this electron donating group. If you just basically push these electrons out again. So you have OMe here with its lone pair. And then you have a double bond at this end, the lone pair here on this carbon atom, and you end up with a positive charge here. And just as a reminder, this is exactly the polarization that we had drawn in previously, where we basically had delta minus, delta plus, delta minus, delta plus, and delta minus, right? So this delta minus and this delta plus and this delta minus here correspond essentially to the negative partial charge and the positive partial charge that you can derive from the resonance structures. Now, the same, of course, works for the dienophile. So if you were to draw our alpha beta unsaturated ester again, we can push the electrons in the system the same way as we've done it before. So we could push these, for example, in here, and we could push these electrons out to the oxygen. Then you would have a negative charge here on the oxygen, ethyl, and then you would have a positive charge at this end of the pi system. And if you wanted to, you could basically move this negative charge out again. So you could move this one over here and take these electrons and move them into your carbonyl again. And that would give you a structure that's very similar to the polarization that we have drawn in before. T, so you have a positive charge here and you have a negative charge at this alpha carbon. And remember, this is exactly the polarization that we had derived just previously, where you have a partial negative charge here, partial positive, partial negative, partial positive. And this partial positive corresponds to this in the resonance structure, and this partial negative corresponds to this negative charge in the resonance structure. Now, there are, of course, other possible combinations that you could put in place. For example, the electron withdrawing group could be located on the diene rather than the dienophile. And we call these reactions usually Diels-Alder reactions with inverse electron demand. So Diels-Alder reactions with inverse electron demand. And just to give you an example, all I did right now is swap the substituents out between the diene and the dienophile. So let's say we have the ester attached to the diene, and we react this with the dienophile. And in this case, let's put the methoxy group, so the electron donating group, on the dienophile. So here you have electron donating group. Here you have the electron withdrawing group. And we can play the same game with the system here again. And if you count through, this carbon is going to be positively polarized. That means that neighboring one is going to be delta negative, delta positive, delta negative, delta positive. And if you go through this here again, it's the same thing. Oxygen is negatively partially polarized. That means that this is delta positive, and this here is delta negative. So the combination that you would get out of this, again, is basically the positive reacting with the negative end here, and the negative end here reacting with the positive end over there on this side. So again, you get the product that shows the 1,2 substitution on the 6-membered ring. So I'm just gonna draw this out here. So let's say CO2 ET and OMe. And of course, we expect the enantiomer of this too. All right. So in this case, basically, we just swapped the polarization of these partners out. We had an electron poor diene and an electron rich dienophile. So no matter how these substituents are actually distributed between the two partners, the diene and the dienophile, you just have to follow this mnemonic of the polarization to figure out which ends of the pi system will be favorably reacting with each other. Now, we figured out how this leads to a selectivity now. I think the next important point is to ask us, why are these reactions, these polarized reactions, actually more favorable? And this is something that we're gonna have a closer look on the next slide. So let's move this over here. So why are these reactions more favorable? And again, what helps us understand this is to look at the effect that these electron donating and electron withdrawing groups actually have on the orbitals that are interacting with each other. In order to analyze this, let's draw again out our energy diagram of the interaction of a diene with a dienophile. I'm not going to draw all the orbitals in here. Again, I think we've done this often enough. All I'm going to do right now is basically just draw in the energy levels. And let's look at the naked unsubstituted diene and the naked unsubstituted dienophile first. So this is a reference line here that we can draw through this. Okay, so the diene we already know is going to have 4 orbitals that are symmetrically spaced above and below this reference line. So, and if we fill them in with 4 electrons, we have a scenario that looks like this. And our highest occupied molecular orbital of the diene is going to be this one here. On the dienophile, we have a very similar scenario. We have just 2 orbitals, the bonding linear combination and the anti-bonding linear combination. And in this case, only this one is filled. So this is again our HOMO. And this is going to be our LUMO. We can draw LUMO here too. Okay. All right. So the possible combinations of interactions that we have discussed so far would have been that we can take the electrons in this HOMO and have them interact with the lowest unoccupied or empty orbital of the dienophile and form a bonding linear combination and an antibonding linear combination. Or we can do it the opposite way around, where we take the empty orbital from the diene and react it with the filled orbital of the dienophile. Now, this is kind of like the combination of the possible orbital combination that we have discussed during last class already. What we bring in this time as kind of a new concept is what happens when you actually put electron donating or electrons withdrawing substituents onto these dienes and the dienophiles. So let's look at the example that we had just now. And I'm just going to keep this very generic. I'm just going to write here an electron donating group. So nothing specific. It could be a methoxy. It could be anything that is electron donating in this case. So what happens to these orbitals as you put an electron donating group on there is that the energy of these orbitals are shifted upwards. So they go to higher energy. So this one moves up here, for example, and this orbital moves up here closer to this energy level. And so do all the empty orbitals move up in energy. The population of these orbitals doesn't change. We still retain like 2 electrons in the HOMO and no electrons in the LUMO. And let's say here HOMO. But what changed is that the relative energy with respect to this reference line here, these orbitals moved up or moved closer to this reference line. Now, what happens on the other side with this other partner? So let's say we have an electron withdrawing group on this system now. So EWG, so this is, for example, an ester, a carbonyl, or an aldehyde, or something like that. Now, the electron withdrawing character of this group stabilizes this pi system, and the stabilization is reflected in the fact that the energy levels go down, so they drop. So in this case, this one, for example, goes down in energy and ends up roughly here. And this one goes down in energy and ends up roughly here. And again, the population of these orbitals stays the same. But what changed is the relative position of these orbitals. So this HOMO dropped down and this LUMO dropped down. Right? And if we start now looking at possible combinations or linear combinations of orbitals, we can still pick the same combinations as we had for the unsubstituted systems, but there's clearly now a preference for one interaction that is much, much more favorable than the other combination. So if you look closely, this HOMO here is now much closer in energy to this empty orbital of the diene. So this is, the dienophile, that's basically this one here, the LUMO of the electron withdrawing pi system. So this interaction here, let's draw it out, will be much more favored because they are closer in energy, and the interaction is much, much stronger between these two systems. Now, the other combination is so this is basically a better interaction between these orbitals now, and that facilitates the bond formation. The other interaction, the other possible interaction where you react the lowest unoccupied molecular orbital of the diene with the highest occupied molecular orbital of the dienophile, this distance between these orbitals increases. So this becomes less favorable, right? So it's much less likely that you're going to get this combination, and most of the interaction will essentially come from this interaction between the HOMO of the diene and the LUMO of the dienophile. And we can draw here. We can write something like smaller gap, faster reaction. So bottom line, what these substituents essentially affect on the pi system is that electron donating groups raise the orbital energies. That's what we observed here by pushing these orbitals up in energy. In electron withdrawing groups, lower all orbital energies. And that's what we've seen here, where these orbitals drop down in energy as you put an electron withdrawing group on there. And now the key, the key realization that comes out of it is that Diels-Alder reactions run faster and better the smaller the gap between the HOMO and the LUMO is going to be. So if we have the right polarization, Diels-Alder reactions have smaller HOMO-LUMO gap and therefore faster reactions. All right, so again, the key factor here is essentially this difference in energy between these two energy levels. So this is the gap that we have been talking about. All right, so now that we've talked a little bit about the effect that substituents have on the system, there's an additional factor that we have to consider once we actually incorporate substituents on these dienes and dienophiles, because the relative orientation of these substituents can lead to different isomers of this reaction. So let's take a little bit a closer look at that. The stereochemistry, essentially, of Diels-Alder reactions. So this is 24.4, stereochemistry of Diels-Alder reactions. Reactions, there you go. Now let's look at a very simple example that is fairly easy to understand, where we react essentially a cyclopentadiene with a dienophile. So let's say we have, let's draw this actually in perspective a little bit to make it easier to see. So we have cyclopentadiene, and we react this with a dienophile that now has let's say one electron withdrawing substituent attached to it. Let's say here we have the double bond and we have a hydrogen pointing out into this side, and then we have an electron withdrawing group attached to the system. Now I've already drawn it in a structure that is reminiscent of the transition state of this reaction. So I can use the brackets and the cross to designate this as the transition state. So if you now basically start forming a bond in the transition state between this end of the pi system and this end of the pi system, and from here, this end of the pi system interacts with this side, then you get out a product that we call usually the exo-isomer of this reaction. So draw this out like this, and then the hydrogen points downwards, and the electron withdrawing group here points upwards. We call this usually exo. And if you want to think about this in a little bit more planar conformation, or easier drawing maybe to see, we have this methylene bridge coming out towards you, and then we have the electron withdrawing group here coming out of the plane, and the hydrogen going back behind the plane. of the system. Now we missed a double bond here in both cases. Okay, so these are kind of the two, so this is basically the exo product that we can expect to see from this transition state. However, if you think about this carefully, this is not the only transition state that you can potentially form between this, because I decided arbitrarily to put the hydrogen underneath this pi system and the electron withdrawing group on the outside of the pi system. Well, you could make the argument that maybe there is some steric congestion between this, whatever you put under the pi system here, and the pi system itself. So that's why the electron withdrawing group is pushed out further away from this side of the ring. So you might say that thermodynamically, this might be the favorable product. However, it's worthwhile investigating the other interaction too. So we again can draw our 5-membered ring here. And this time we just basically swap this around. We have our double bond again. This time we push our hydrogen out here and we put our electron withdrawing group, we tuck it underneath, underneath the ring. Now we can do the same experiment now from the transition state. You can form a bond between this end of the pi system and a bond with this end of the pi system. And the product that you get out of this, again, is a bicyclic ring system. So this side of the ring system doesn't change at all. But on this side now, the stereochemistry at this position is inverted. So the hydrogen comes up and the electron withdrawing group points downwards. So if you looked at this in the planar projection again, the methylene bridge comes out towards you, and then the hydrogen comes out towards you, and the electron withdrawing group points towards the back. Now, the relative conformation of this electron withdrawing group, we usually define this as the endo product. Endo because this electron withdrawing group was tucked underneath the ring system. And these two products with respect to each other, if you take a close look at them, they are actually diastereoisomers. So they're not enantiomers because this bridge stays the same, but the stereochemistry at this carbon atom essentially is just inverted. Right? So they are relative to each other, they're diastereoisomers. Now, if you just have a look at the structures, you could potentially make an argument for this exo product being more stable based on sterics. So the interaction between this electron withdrawing group and this methylene bridge is less than the interaction of this electron withdrawing group and this this olefinic large bridge over here. So you could say like, well, maybe this exo product is thermodynamically favored. It turns, however, out that if you run this, this reaction under kinetic control, that you usually favor the formation of the endo product. And this is something that we're going to have a little bit of closer look at now, where this selectivity comes from. So exo is thermodynamic product. So the more stable product, and the endo product is the one that is faster or formed faster in this reaction. So this is the kinetic product of the reaction. So this is endo product is formed faster if you run this this reaction. So why is this? Well, we can have a closer look at, again, the orbital interactions of this system, and I'm going to pick a simple pi system in order to make this easier to understand. So why the selectivity exo versus endo. And the model system that we're going to look at is just a simple reaction of diene with a polarized dienophile. So let's just simply take an aldehyde here because it makes the drawing of the orbitals easy. You can basically treat every possible substitution pattern the same way. I just picked this example because it's easy to draw and easy to see how the interaction is going to work out. So in order to figure out how this works again, well, let's draw our orbitals. So again, we have our diene on one side, and we know how these orbitals essentially look like. You have phi 1, which are all in the same shading. Then you have phi 2, which has one node. You have phi 3, which has two nodes. And then you have phi 4, which has three nodes. And we know that these orbitals are half filled. So the bottom ones have 4 electrons in there. So this is our HOMO. And this here is our LUMO. Now this is interacting now with a pi system that is essentially this this alpha beta unsaturated carbonyl. And in the first approximation, I can treat this essentially as also a diene. Just imagine for a second that this is not an oxygen, but this is essentially a methylene group again. So there's a p orbital here, one double bond and another double bond. The only difference with respect to the orbitals here is that this one is electron withdrawing, so it's lower in energy. So basically it looks exactly the same, just that the orbitals are shifted downwards a little bit. So let's draw it like this. And again, we have the orbitals populated like this. And if I can draw it out, these orbitals look exactly the same. So we have the filled ones. Just as a quick reminder, I'm going to mark just one of these here as the oxygen. So let's say this is the oxygen of our aldehyde, right? So this one was diene, and this one, let's draw this out. This is the oxygen here. Okay, so again, we are going to do, we're going to make an interaction between two of these orbitals. And if we take a closer look at the possible combinations that we can deal with here, HOMO, and this is the LUMO. The lowest gap between orbitals is again between the highest occupied molecular orbital of the diene and the lowest unoccupied molecular orbital of the dienophile. So this is the smallest gap between these two, and this is the favorable interaction that we're going to be observing in this system. So now that we know which orbitals are actually coming together, we can draw out the transition state for that. So in the case of the diene, we have phi 2. And if we take a closer look, this is alternately shaded and has one lobe in the middle. So this looks somewhat like this. So we can call this the HOMO. And on the other side, we have the the lowest unoccupied molecular orbital of this combination. And we can simply draw this out. Let's draw this underneath here. So let's draw it like this, and let's put the oxygen over here. And we can draw the lobes in. So, and if we pick the correct shading, this now has 2 nodes in the system. So 1 node here, and 1 node between the carbon and the oxygen here. So this is going to be our LUMO. Now, the primary interaction that we are going to be observing now is the interaction between these 2 orbitals here and the interaction between these 2 orbitals here. That's our primary interaction in the Diels-Alder reaction that then gives us the product. So this is primary interaction. All right, so if you take a closer look at the type of transition state that I drew out here, it's essentially reminiscent of the exotransition state, where the hydrogen here is tucked under the pi system, and this electron withdrawing group, so this carbonyl here, ends out basically sticking out away from this pi system. So we can call this here essentially the exotransition state, exotransition state model. Right? So we only have this primary interaction. Now, if we try to basically do the endotransition state, all we need to do basically is take this pi system down here and just turn it around so that basically this carbonyl ends up lying underneath this diene. And we can draw this out again. So this was the exotransition state. Now we're drawing the endotransition state. So we have our pi system here again. This remains unchanged. I'm just going to pick exactly the same shading here. So this was our HOMO again. And now I'm going to draw the other pi system underneath it. And this time I'm basically just going to tuck this carbonyl in underneath this other pi system here. So let's draw this like this. Let's say the oxygen is going to be over here. So I have a node, another node, 1 node here, and 1 node here. And now I can look at the shading again. I know that this is the lowest unoccupied molecular orbital, so it has 2 nodes in it. This is going to be shaded, this lobe is going to be shaded, and this lobe is going to be shaded. Now, if I look at the possible interactions again, let's draw quickly LUMO here. We again have the primary interaction that forms the new carbon-carbon bond between these 2 lobes, right? So this is the new carbon-carbon bond in our primary interaction. But what I see additionally, or what I can glean additionally from this picture, is a secondary interaction where I have this unshaded lobe here that comes close to this other unshaded lobe and can form another favorable interaction. That this does not lead to a bond in the product, but it lowers the energy of the transition state and makes this the faster pathway towards the product. So this is secondary interaction. And all of this is basically described in the endo transition state model. So the reason that the endo transition state is favored kinetically is because you have the secondary interaction between the lobe here on the lowest unoccupied molecular orbital and this lobe here on the highest occupied molecular orbital that you can't form on this side of the system because this residue points away from this pi system. If you tuck this underneath it, you can benefit from this additional interaction, and this overall lowers your activation barrier and makes this reaction faster through this endotransition state than through this exotransition state. So bottom line is, endotransition model is a fast reaction, and through the exotransition state, it's a slow reaction. All right, so now the fact that the endotransition state is favored is counterintuitive when you just look at the steric effect. So you could say basically the steric bulk from this additional substituent that you tuck underneath it will be repulsive. But since the orbital overlap matches perfectly, you get stabilization out of this, and that lowers the energy of the transition state. So let's do a practice where we try to figure out all these effects coming together. So the electron donating and electron withdrawing groups, and the endo and exo transition states, how they affect the product distribution. So let's pick a simple example here. Well, it's not that simple actually. So, but it kind of illustrates all the issues. So let's say we have a methoxy group, and then just for keeping track of everything, I'm going to draw in all the hydrogens in this case. So we have this diene, and we are going to react it with a dienophile that looks, let's do it like this. Let's make a ketone out of it, methyl group here, and then we're going to do a methyl group on this side, and we're going to have the hydrogens here and here. All right, so what is the first thing that we need to figure out? Well, we need to figure out which is the diene and which is the dienophile. That's pretty simple. This is the diene, this is the dienophile. The diene has the electron donating substituent, the methoxy group here, and the dienophile has the electron withdrawing substituent, which is this ketone here. So it's a Diels-Alder reaction with normal or regular electron demand. Now, if we try to figure out which of these ends of the pi system are going to react with each other, we can again use this trick of looking at the polarization. So in this case, we know that this is negative, positive, negative, positive, and negative. And then on the other side, we can do the same thing. So this is negative, positive, negative, and positive. So we know already that this end will form a bond with this side, and this end will form a bond with this side. So after we figured that out, yes?
Oh, could you click off the notification for your calendar? It's kind of blocking the second structure.
I wasn't clear that you would be seeing that. Let me see if I can change that. Screen. It's still there, right?
Yes.
That should have fixed it. Yeah. Okay.
Thank you.
All right, back to this. So we were talking about trying to figure out like what the combination is going to be for the system, and how we have to draw the transition state to predict the products of this reaction. Now we already know which ends of the pi system are going to react with each other. We drew this out there and determined this based on this partial polarization. Now, the next thing we need to do is try to figure out how to draw the transition state for that. And there, the best method is essentially to draw it exactly the way that we have done just a second ago, where we basically place them just atop of each other. In this case, OMe goes to the back, and we have the hydrogens out here. So you have something like this, right? And then you can place your diene underneath this or above this pi system. This is basically up to you, and it gives either of the enantiomers in this case. I'm going to place it underneath it just to be consistent. So here is the double bond. And now we have to be careful trying to figure out how we place basically this, this carbonyl here, because that's the one that's going to give us the secondary interaction. So we want to take this part of the molecule and tuck it underneath this pi system so we can take advantage of the stabilization of the transition state in the endo conformation, right? So essentially, what that means is that I basically take the carbonyl here, methyl, put this over here, and on the other side I have the hydrogen, and then the methyl group points out here, and I have this on the other side. So keep in mind that we have to keep the stereochemistry around the double bond the same, of course, right? All right, so all we need to do now is basically figure out which ends are reacting with each other. We've done this up here already in this conformation. Now in the transition state, we basically just have to figure out that this end reacts with this end. And then maybe we put this green. We can have this end reacting with this end of the pi system. Draw a dotted line here. And this is our transition state of the reaction. And if we draw the product that comes out of this, we basically can just follow the new bonds that we are forming and determine what the stereochemistry is at this position, at this position, at this position, and at this position. So those are the key factors that we need to figure out. So we know that we get a double bond here. It's a simple cyclohexene. Now, if we form a bond between this carbon atom and this carbon atom, this hydrogen here ends up on the top side of the molecule, and the methoxy group ends up on the back side of the molecule. So we can basically draw the methoxy group here towards the back. Now, how does it look like with this system here, at this carbon atom? If we form a bond between these two, the hydrogen is again on the top side, and the aldehyde, so the ketone here is on the back side. So we can draw the ketone here again. And then the last one that we have to pay attention to would be these two. Here we have the methyl group that is going to end up on the opposite side of this ketone. So if this was down here, this methyl group has to point upwards. And up at this position, we just have two hydrogens, so there's no stereocenter here, so we don't have to worry about the stereochemistry at this position. Now, this is not the only product that you can get out of this, because remember, this is always a racemic mixture of enantiomers. So if you want to be precise, you can basically draw the second enantiomer that you expect from this reaction. That looks like this now. Basically, all the centers are just inverted. And Me. So what would you have to do to draw the transition state that leads to this product? The only thing you would have to change in this transition state is basically the relative position of these two pi systems with respect to each other. So I arbitrarily decided in this case that I was going to draw the dienophile underneath the diene. Of course, I could have basically taken this system and placed it at top of this. So if I drew the diene below the dienophile, I would have gotten this as the major product. And since these are equivalent, essentially, the positions or the probability that I'm going to adopt either of these positions, I'm going to get a racemic mixture of these two enantiomers out of the reaction. Now, figuring out the stereochemistry of these systems is a very important skill that you guys need to learn, and there's good practice problems in the textbook, so I strongly encourage you to do those. I will just give you two more here to help you practice your skills a little bit. So these are examples that you can practice at home. So we're just going to pick something that looks like this: OMe, OTMS, so it's a trimethylsilyl group. And then here I'm going to have a hydrogen and a methyl group. So it's a higher substituted system here. And I'm going to react this with something that looks like this, and I'm going to have a methyl group over here. So again, this is the diene, this is the dienophile, and what you need to figure out is what the product of this reaction is going to be. Of course, you expect to see two enantiomeric products in a racemic mixture again. Now, the other example that I want you to practice is something like this. So this is a furan, and you can react this with, let's see, ethyl group here, and let's put a nitrile here, and let's put on this side a phenylating. And try to figure out what the product, the two enantiomeric products of this reaction are going to be, right? So we have a couple of these problems also in the problem set. This is basically just to practice what we have gone over the first part of this lecture today. Okay, I want to end up with another type of 4+2 cycloaddition that is quite common in organic chemistry, and this is the 1,3 dipolar cycloadditions. And in your textbook, that's 24.7, and that's the 1,3 dipolar cycloaddition. Now, as the name already says, it deals with 1,3 dipoles as part of the reaction, and but it still falls under the category of these 4+2 cycloadditions. So it has some resemblance with the Diels-Alder reaction. Now, I'm just going to show you one prototypical example. So again, you have an olefin, so there's a 2-pi component that reacts with something that has 4 electrons. So let's say this is 2 electrons, and the partner that we react is this 1,3 dipole, and I'm going to keep it very generic here. I'm not going to even use specific atoms. I'm just going to use positions and call them A, B, and C. So let's say A, B, and C, and let's draw it like this, and we give this a positive charge, and we're going to give this one here a negative charge. So that's where the 1,3 dipole naming confirmation comes from. Now, the number of electrons that are participating on this side here are 4 electrons. So it's basically the electrons here. So this is 2 electrons, and we have the electrons over here, which are 2 electrons in a lone pair. And the classical way that you can think about this is if you push the electrons around in this system, you can take these and move them over here. You can take these electrons out of the double bond, move them over here, and you can take these electrons and move them into this atom B. And what you end up with is a generic structure that is now part of a 5-membered ring where you have atom A, atom B, and atom C fused to what was previously this olefin. Now this again is a 6-pi reaction, so a total 6 pi electrons, and it follows the classical 4+2 cyclization rules. Now, there is another version of this that looks a little bit different. It again has basically 3 atoms, but they are this time connected in a linear form rather than this band conformation that you see here. So again, we have A, we have B, and instead of a double bond, this time we have a triple bond to our molecule C. And again, you have charges. So this is a negative charge, and you have a positive charge on this side. And again, you can draw the arrows exactly the same way as we have done before. So you can take the electrons out of this, move them over here, take the electrons from here, move them over here, and move these electrons in here. And again, you get structurally a similar molecule out of this, just that this time you have one additional double bond in the system. So we have A, then we have B, and then we have a double bond to the atom C over here. And again, this is still a 6-pi electron system and falls under the 4+2 electron rule. So you would have 2 electrons here, 2 electrons here, and 2 electrons here, right? So it still basically falls into the same category of reactions that we are dealing with before. And that we want to look at 2 specific examples of these 1,3 dipolar cycloadditions. Actually 3 specific examples of these 1,3 dipolar cycloadditions towards the end of this class. So the first one that we want to talk about is one that falls into this, this second category where we have this linear 1,3 dipole. So linear 1,3 dipole. So let's pick our cyclohexene again, because it was like a nice building block. And the linear 1,3 dipole that we're going to use in this case is diazomethane. So this is basically a molecule, a methylene group, and you have a negative charge here, and then you have nitrogen attached to that. So if you take a closer look at this, you probably quickly realize that this is going to be a hell of a reactive molecule. It has this classical 1,3 dipolar structure. So remember, you had like A, B, C atoms in the example on the last slide, and you have a negative charge here, you have a positive charge here, and you have a triple bond, right? Just to kind of clarify this a little bit, you might be able to draw this out in a different conformation also that you'll see in textbooks. So something like this is just essentially a resonance structure of the same system. So we have positive charge here and negative charge over here. Right? So these are basically just resonance structures of each other, but this is kind of like the structure that resembles the previous standard example that I showed you the closest. So again, you could take here the electrons from this side, react it with this carbon atom, take these electrons and react it with this nitrogen, and take these electrons and move them in here. And the product of this reaction would then be an annulated ring system where you have a 6-membered ring like this, and then you have this fused to a 5-membered ring with 2 nitrogen atoms here. So something like this, right? In the stereochemistry, here is one that these 2 hydrogens end up being on the same side. Of course, you could have done the same way as with the Diels-Alder reaction. You could have arranged these where the 6-membered ring comes to rest above this pi system or below this pi system. So you always get the 2 possible enantiomers out of this reaction. So the other product that you expect to see from this is the one where the hydrogens are just pointing to the other side. And that depends on how these molecules essentially come together in the transition state. Now, another common one that is very useful, especially for the synthesis of heterocycles, is a nitrile oxide. So nitrile oxide. So this looks a little bit like, let's see, let's draw CN. So this is a nitrile essentially. I can put a methyl group over here. And nitrile oxides are essentially the molecules that are oxidized at this nitrogen atom. So you put another oxygen here. They look a little bit funky, but they are 1,3 dipoles again. If you count the electrons, you have to place charges on these, of course. And these can react with other olefins or alkynes, so other pi systems again. So let's pick a simple one. Let's just pick a simple alkyne here, R. And again, we can draw the arrows out. So arrow from here to here, and arrow from here to here. And what this gives us essentially in one quick swoop is a heterocyclic system, 5-membered ring system that looks like this. So let's say nitrogen here, oxygen, double bond, and then we still have a double bond over here. We had attached a methyl group on this side, and we had 2 residues R and R over here. And this happens to be an oxazole heterocyclic ring. But the important thing to recognize is that even though these look a little bit like funky molecules, they react exactly the same way as in the Diels-Alder reactions, where you have 2 pi electrons shared between these 3 atoms, reacting with the olefin on this side, or the alkyne on this side, as the 2 pi electron species. Now, the last one that we want to go over that is relevant to these 1,3 dipolar cycloadditions is a reaction that is called the ozonolysis. And that's actually synthetically a very, very useful reaction. So 24,8 is ozonolysis. And what this reaction essentially does is that it cleaves double bonds. So it is an example of a cycloaddition reaction. That's why we cover it as part of this chapter. But what it essentially does is you take a double bond and you treat it with ozone. So that's O3 essentially, right? That's the thing that's in the ozone layer. In usually DCM, at low temperatures, minus 78 degrees Celsius is very common. And then in a second step, you treat this with a thioether, usually dimethyl thioether, or triphenylphosphine, or another alternative for the workup is zinc and acetic acid. But what you get out of this is essentially a cleavage of this double bond at this position here. And each of these carbon atoms that you're left with at either side of this double bond are going to turn into an aldehyde. So on this side of the system, you're going to end up with something that looks like this. And of course, if you hark back to our chemistry that we talked about in the first couple of weeks, in our second semester of Introductory Organic Chemistry. If you have a base present in this system, you're going to do a condensation or deprotonation of this position and condensation with this aldehyde. So the product of this reaction oftentimes is then the aldol addition product or aldol condensation product that looks like this. So the last part is the aldol condensation. If you have a base present, of course. Why does it keep showing me this? All right, so now let's take a little bit a closer look at the mechanism of this reaction. And the first step, obviously, is already a cycloaddition. So if we have our starting material here, and now we do the 1,3 dipolar cycloaddition with ozone. Ozone looks like this. Oh, positive charge here and negative charge here. So it's a 1,3 dipole, one of these bent 1,3 dipoles that we have talked about previously. And we can again take the electrons from here, react with this side, electrons from here react with this side, and electrons from here react over there. And we get the 1,3 dipolar addition product, or what we call the primary ozonide. So this is a 4+2 cycloaddition reaction, and we end up with something that looks like this: 3 oxygens, each of them with lone pairs. And we call this primary product the primary ozonide. Now, remember that what we really want to do is break this, this bond here. So we've done part of it already. We've broken the pi system, but we still need to break essentially this new carbon-carbon bond. And that works via a mechanism that is essentially the reverse to this 1,3 dipolar cycloaddition, just that I'm not breaking these bonds now. These are the ones that we just formed, right? But I could break, for example, this one and this bond here. So the way I could draw this out then basically is take these electrons and push them over into here, take these electrons and push them over into this system, and take these electrons over here. And this would give us essentially a retro 1,3 dipolar cycloaddition. So it's basically the reverse. So we can say retro 1,3 dipolar cycloaddition. And the product that I get out of this is now the one that already has this critical carbon-carbon bond cleaved. On this top side here, I'm going to end up with a ketone, or in this case, sorry, an aldehyde. On the bottom side here, I'm going to end up with something that looks a little bit more exotic. But if you take a quick look at it, that's basically just, again, a 1,3 dipole, negative charge here, positive charge over there. Now, this species or this functional group down here is called a carbonyl oxide. Carbonyl oxide. Now, all I need to do in order to get this towards the end is basically another 1,3 dipolar cycloaddition. But in order to see the product of that, what I'm going to do is I'm going to redraw the structure a little bit by simply having it rotate around this bond. So this is essentially just the same structure that I redraw down here, but I have rotated around one of the bonds to make it easier to see. So this, and then I'm going to draw this aldehyde down here, and up here I'm going to draw No, this is a carbon, sorry. So it's a carbon, oxygen, oxygen. So negative charge, positive charge. And what I do again is here a 1,3 dipolar cycloaddition of this end with this end, this bond here with this bond, and this one I'll move over here. And this turns into what we call the secondary ozonide. So this looks a little bit different than previously. We have a 6-membered ring here. Now this 6-membered ring is linked by a bridge oxygen atom and then 2 oxygen atoms that come from this part here. So this is what we call the secondary ozonide. Now this is essentially the final product of the first step of this reaction of the ozonolysis. Before you actually add your second reagent, like for example the dimethyl thioether for the workup. So if you add that to the reaction, so dimethyl dithioether, can draw the lone pairs here. What happens is that the sulfur is going to be attacking the oxygen, or one of these oxygens. So I can draw something like this. And this here is going to break this oxygen-oxygen bond so that you have a negative charge on one end. The product out of this is going to look like this. Still have O here with a negative charge now. And on the other side, we have O attached to the sulfur with the 2 methyl groups here. And this, of course, now has a positive charge attached to it. And this can simply break up during the workup step. These electrons can be pushed in here. These electrons can be pushed over here. And these electrons can be pushed over here so that we form, or we essentially fragment the system, which leads to the 2 aldehyde functional groups. So this is basically the species that we wanted. And the other fragment here is dimethyl sulfoxide. So negative charge here, positive charge here. And this is basically the solvent that you know as DMSO, right? So this mechanism of the ozonolysis is nothing but just a sequence of essentially 1,3 dipolar cycloaddition, a retro 1,3 dipolar cycloaddition that gives you this product here. This is basically just 2 isomers. And then forward again, a 1,3 dipolar addition to form the secondary ozonide. And after that, you basically get the workup of this reaction that leads to the 2 aldehydes at the position where you previously had the double bond and a small fragment like DMSO. Now, what you can do as a practice, do the same reaction, and instead of dimethyl thioether, use triphenylphosphine as a workup. It works exactly the same way, just the product that you're going to get out of it is something a little bit different than DMSO. But the mechanism here, the phosphorus attacks one of these oxygens, is exactly the same thing as previously. Okay, I want to end here. We're going to have, I think, one more lecture on cycloaddition reactions next week, where we're going to talk about electrocyclizations. And no, so this Thursday, yeah, this Thursday we're going to end with that. And then we are going to start moving into radical reactions in the last 2 lectures of the semester. As usual, I have my office hours in just a couple of minutes. I might be a little bit late because I have to compile the file here, but I'll upload this lecture as soon as it is ready in the usual Dropbox. Okay, see you on Thursday.